first talk. Yeah. I should have computer. An epic fail, my God.
Okay, you went for that part. That was worth it.
Okay, so let's start the second block of the session, and with Sam is going to tell us about flexible instruction set semantics.
Okay, so the title on my slide and in the program is actually wrong. The correct title is, Can I give a talk despite a 9-hour jet lag? But I'm going to prove you that yes, I can. All right. Okay, so in our lab, we write verified software and verified hardware and want to compose these things together into a whole end-to-end verified systems stacks. And to do this, one important part is really this instruction set architecture, which really is the interface between the software and the hardware. So an important question is, well, which instruction sets do you pick? And previous projects have used variations of or simplifications of x86 or ARM typically, but now recently in the landscape has appeared RISC-V, which is a whole new thing. Because it's actually an open standard. And I was super surprised when I learned that this is a big deal in the sense that most other big commercial instruction sets do not even publish the standard for openly. So you have to pay license fees and NDAs and everything, even to know what is the specification. Whereas RISC-V, the specification is open and governed by somewhat neutral body that maintains this standard. And it's also new, simple, clean slate design. So this is really the optimal vehicle to do research. And there's plenty of open source implementations as well as commercial implementations. And the tooling ecosystem has also been adopted. Many big useful tools have been ported to RISC-V. And recently also Google has announced that Android will support RISC-V as an instruction set, among only very few others. So the goal that we have is to create a flexible RISC-V specification that supports many different use cases, such as testing and simulation, model checking, but also formal verification in an interactive proof assistant. And our approach that we chose was to rely on existing languages and tools instead of reinventing new languages and tools. So said differently, what we want is a formal semantics for a real-world instruction set that supports a wide variety of different uses at a reasonable effort. And the claim that I want to make here, and ICFP people might appreciate, is that this can be achieved solely with a general-purpose functional language using as key ingredients monads and type classes. So compared to other past efforts, they are like not as flexible as ours or rely on DSLs. And the main alternative that I will have to talk about, obviously, is the SAIL DSL, which has been chosen as the official formal RISC-V certification. So as our general-purpose functional language, we chose Haskell, and we used the main vehicle for getting this flexibility is a type class that we call a RISC-V machine, and it contains a number of primitives that forms the vocabulary that we need to express the specification of individual RISC-V instructions. And then each of these white boxes is a different instantiation of this type class. And we also have chains of lifting and extending type classes. A little more detail about this central RISC-V machine type class. It takes two parameters. The first one is P, which must be a monad, and but this one is like a can be a different one for each instance, as in for each use case. And then it takes a T, which is the type for integers that appear in a register, and it will be instantiated with int32 or int64, depending on the bit width of the machine. And here's a little functional constraint for those who like it. This is the list of primitives that we need to express the specification of RISC-V instructions. You can see there's what they are about. What setting and getting a register is. They are loading and storing 1, 2, 4, or 8 bytes from and to memory, and getting and setting a PC, and a few more of them. For integers, we made a somewhat unusual choice, but I think one that we like, which is we only distinguish 2 types of integers. The first one is signed and unsigned integer of a certain number of bits. And the second one is an integer in the machine's bit width. And for the first one, we called that machine int, which just means some integer inside the machine of any bit width. And it turns out that in this specification, 64-bit happens to be enough. So we just make it an alias for that. And for efficiently simulating, this will be very convenient. And the second kind of, for the second kind, we use this T that appears in the type class. And this is in contrast to other approaches which say, well, you have to use dependent types to track exactly the bit width of each integer. And we chose not to do this, I think, even though, or actually because, one of our co-authors wrote this whole book about how to use dependent types in Coq. So a little overview of how our spec is written. We have a decoder which defines, first has to define ADTs for RISC-V instructions with like some fields, and you can see, for instance, the immediate values or machine int, even though, so you get 64 bits, even though the spec is written in such a way that only 12 bits matter for this for the offset in store word, for instance. And then we have a decode function which takes an instruction set which tells which extensions are active, and then it takes an instruction which is just 32 bits, but actually represented using 64 bits. And then first we name a few relevant bit fields, and then we check the values of these bit fields, and depending on these values, we create instructions such as store word or a branch on equality. And then the other important part of the specification is the execute function. So for each instruction, we define what happens if you execute it. And as you can see, we expressed it in terms of the primitives that I showed you before. So get register, get PC, and set register, and all these are all these kind of primitives. I think raise exception with info is another helper function that is expressed in terms of the primitives that I showed you. And we tried really to make this basically just, if you squint hard enough, corresponding to the official PDF spec. And there we aim to provide, to cater to 2 different kinds of readers and users of this spec. The first, more casual users don't even need to know Haskell. They could just read this as a funky version of English, and just kind of see what it hopefully what it does. Whereas more seasoned Haskell users will certainly want to know that the definition, the signature of execute has this type, and they can dig into more detail and also understand why there's do and monads and everything of that. Now I want to go through a few different use cases, and for each of them show you how we instantiated this RISC-V machine type class with an instance tailored for that use case. And these are the use cases that I will go through. So expressed on this diagram, I will start with testing and simulation. So it's fairly standard things. We instantiate the monad with the IO monad. We use references and arrays because we want to be reasonably efficient. And with that, we managed to run at about 100K instructions per second. And we managed to boot Linux. And we also managed to run each like small tests that for each RISC-V instruction. And maybe the image is gonna come back.
Yeah.
Yes, it does. And we use this extending type classes. Basically, we start with a simple instance, and then using some lifting, we can add additional features such as exceptions or memory mapped I/O by lifting all the operations that don't change and adding like one more operation that uses the added capability of the monad. Now, the next part is the interactive theorem proving. So for this, we used a tool called HS2Coq, and it takes, we feed most of our Haskell sources into it, but what we really want is, we really want to control the kind of spec that we get. So we do have to use a feature of HS2Coq that is called edit files, and these allow us to map certain definitions from Haskell to something in Coq that we can freely choose. For instance, for the machine int, which is a 64-bit integer in Haskell, we chose that in Coq it would be more convenient to use unbounded z, because that's a very easy to use data type in Coq. And since we know that in the specification in Haskell we don't rely on any wrapping, but properly masked all the uses, this is actually semantics preserving. Like this, we create a code base called RISC-V Coq, and it turns out that there's also some other Haskell sources which would need so much configuration and tweaks to tell what result we actually want to get, is that it's just honestly much easier to manually translate, rather than writing a super advanced translator that special cases all these cases. So it's a pragmatic approach here. And then the cool thing is that this RISC-V Coq specification, we were able to use it as the interface between our Bedrock 2 verified compiler and our verified Kami processor. And I think this should be the main test case for such a specification. And as far as I know, we're actually the only ones who did both sides for industrial strength instruction set architecture. So like this, we can use the whole thing in our end-to-end verified stack and have resulting in an end-to-end theorem that only mentions the top level, high level behavior and the hardware description language semantics. Now in this in Coq, the question arises, which monad should we pick? And the first thing we tried was non-deterministic state monad with error. So always for options, state is state, and Andy is non-deterministic. And you can give this type. So S is the initial state. Then this A is an answer type. S is the new state. And arrow prop means basically think of it as adding a set that adds the non-determinism. This is the type that the type itself makes sense. You can define a bind on this type. It's a little gnarly already. Return in exchange is easy, but then All of our development, including the compiler, is based on weakest preconditions. So we need something to say, when does a monadic computation satisfy a postcondition? And I call this mCompSat, for monadic computation satisfies postcondition. And again, you can write this with a lot of quantifiers, and it worked, but it was just pretty cumbersome overall, because basically the problem is that each bind creates a OR here, and it creates an exists. And most of these ORs and exists are what I call fake, in the sense that only one side is possible. Basically, most operations, most bind operations are successful and can't fail on the first thing. And also, the existentials are often fake in the sense of there's only one value that's possible rather than many of them. And overall, this just led to huge and cumbersome formulas. And this mCompSat doesn't help in story either. So in order to keep this manageable, we needed to add some kind of creation and inversion lemmas for all operations. And it worked, but was cumbersome. And then the question is, well, given that all we need or want is weakest preconditions, can't we define this more precise, more directly? And it turns out that yes. So the second approach which we tried and liked much better is based on the free monads. So the first step is to write the RISC-V machine instance, which is a very, very dumb instance. We just basically materialize these primitives into AST, one for each primitive. And we also have a free monad which just materializes the bind and the return. And after using this trivial instance, we can add an interpretation function that goes from this AST to a signature which looks like a weakest precondition. Maybe you like the argument order swapped, but I like this to be the initial state, this the desired postcondition, and then a prop which tells me whether the desired postcondition actually holds. But you can also flip the arguments and to see it more as a predicate transformer. This one works much better. And so next application is some experiment for memory model explorations. So we are following algorithm called HMC presented at ASPLOS, and this algorithm allows to efficiently enumerate all possible weak memory graphs, and we implemented that algorithm as a type class instance of our RISC-V machine instance, and the main meat is basically in load word, store word, and fence, and then we can take some litmus tests, which basically execute like two or three instruction programs in parallel, and then use the official RISC-V weak memory formal model that was specified in Alloy. And these functions here query the Alloy analyzer to know which executions are possible, and at the end we can output whether the condition of interest that was indicated in the litmus test can or cannot happen. And finally, another application is model checking our specification against another RISC-V specification, but this time written in Verilog. So for that, the Verilog specification in question is by Claire Wolf, and it's basically very spec-like, high-level Verilog definition of what happens in one RISC-V cycle in Verilog, expressed in Verilog. And we're using this tool called Clash, which can translate Haskell to Verilog, and it's cool to actually have its author in the audience. Very cool. And so we wrote a Clash-specific instance for our type class, making sure that all the data types are very obviously small and very obviously finite, so that Clash can actually generate a circuit for it. And then this worked to use a model checker to check that these are equivalent. And as you can see, it's really, really tiny. So store is just like one value, which is the address, one which is the value that was stored, and then 4 Boolean is indicating which of the 4 bytes are actually affected. It's some kind of mask. And because it's only one cycle, we can do that, and we don't need to model a full memory or anything like that. But there was one snippet which caused trouble, because our specification was geared towards being high level and being as readable as we can. And we rewrote this many times, but basically what we're doing here is we have different extensions, and we collect all the possible decoding results into a list, and then we know that this list of results is always of size 1, or maybe 0 if something went wrong, but we really expect this to be of size 1. And we only did it for the I instruction set, so basically all these ifs should cancel out, and we should get the head of the first. We were only interested in the first element. And we tried to feed this into Clash, but Clash does have to do some normalization in order to create a circuit, and it just ran forever on that problem. So this is the point where we needed to use a pragmatic engineering solution, which was to simply feed this through a little set script and comment out the offending lines. Yeah, sometimes you have to be an engineer. Some related work. Sail is really the main competitor in the area, and Sail is a domain-specific language. And of course, if you make domain-specific language, you can put a lot of super handy little features into it that make your work your life much easier. For instance, they have open variant types that they can scatter over several files, or also the definitions can be scattered across several files. And they have dependently typed bit vectors, and then an asymptotic solver that checks that these sizes add up. So for instance, here, all these numbers here, they actually add up to 32, and the type checker of Sail will invoke an asymptotic solver to verify this for you, which of course will catch some errors that in our case will not be caught. And you have built-in support for bijections, also very cool. And then it's also pretty flexible in the sense that each instruction is usually in its own file, and then on the level of the make file, you can define a few variables, make variables, which tell you which instructions you are interested in. You can pretty flexibly mix and match the instructions you actually care about for your custom specification. But so a big drawback is that they can export coq code, but it just creates 2 files, one of which is huge, and it's just no one wants to use such a huge unreadable file. And this is actually maybe the claim is sure. I mean, the Sail people are not interested in using coq very much. Could probably have more engineering effort to get it done. But there's also something to be said about our approach, whose point is that we rely on the existing work of people. Because, I mean, Stephanie Warwick is sitting here, and she has done all the work of getting HS2coq to work to output palatable coq code. So rather than, instead of redoing all that work, we actually can rely on that work. So to conclude, abstract monads and type classes suffice to write a NISA spec, and you can reuse existing languages and translators, and the shallow embedding that we're using means that we do not need to reinvent and maintain a whole language. Instead, we can just use all of Haskell, and we get a fast enough interpreter for free. But of course, there's a few drawbacks. An important one is that our type class instance cannot, since it's shallow, it cannot intercept or customize the meaning of if then else or of lap. But existing translator like a Clash or HS2Coq can, because they eat the Haskell syntax. And we tried to write a few custom translators instead of just type class instances, but that got pretty gnarly, and because you would have to deal with Haskell syntax and semantics unless your target language is just really following very closely what Haskell does. And this whole thing has been in use for more than 5 years, and we're still using it. It still works. So it works. It works for us. Let's put it that way. So that's it. We have a Haskell source are up here, and the thing translated to Coq is here. And I'm happy to take questions.
So you took the approach writing it in general purpose language Haskell and translating it to Coq, and more common approach will be another way around, writing it in Coq, translating it to Haskell. Mm-hmm. So can you contrast, based on your experience, can you contrast based on your experience these two approaches, and why? Beneficial?
I think it was mostly, I would almost call it political, in the sense that Haskell we thought would be general purpose and unbiased enough to be able to serve as a specification that many people can use, whereas using Coq as the reference thing puts like a very heavy bias towards well, you have to use Coq and you can't use Isabelle, or well, maybe you can, but it would basically put Isabelle users into being a second class and Coq users first class. And I mean, this whole project started when we were trying to become the golden model blessed by the RISC-V Foundation, so there were considerations like that. But other than that, I mean, yeah, I think starting with Coq and doing exporting to Haskell might work even better. I don't know. I didn't try it, but yeah.
Samsung Croc, thanks Vlad for asking the question I was going to ask. I'll ask you my second question. So you've got from Clash an implementation, and you've got your own implementation from Carnegie. So you've got two circuits which should do the same thing. Is that right?
Yeah, I mean the Kami thing goes through BlueSpec, and then BlueSpec.
I was wondering, can you compare them, right? Because can you check the equivalent or comparing performance? Like, what did you get from what was the Verilog like you got from the Clash compared to what you'd get through Kami?
I think I'm not the one who looked at it, so I can't really tell.
We could
yes, you should. Yeah.
Optimizations, and the RISC-V formal has none. It's a spec.
Right.
Yes, that's important. Yeah.
All right.
So Zhong Shao from Yale University. I'm trying to get some idea how thorough your spec is between your work and the cell, because you show the cell has a few megabytes, generate a few megabytes of a Coq spec, and I assume yours is much smaller. Is that right?
Yeah, ours is maybe a little less detailed. We don't have in the virtual memory. We did do virtual memory, but not in Coq.
Right. I was just I'm curious because you can also boot Linux, right? Interpret.
But that's in the Haskell thing. That's not in the Coq thing.
That's right. But your Haskell and the Coq spec are roughly equivalent, though, right? It's modeling the same subset of the machines.
Yeah, I'm not sure how much. No, I think the control and status registers, which is a kind of big thing, I think we simplified that a little bit in Coq.
I see.
We do have proofs where they appear, but I think some simplifications. We don't do virtual memory in Coq.
I see.
So it is a little simpler. But from looking at the Coq output from Sale, it's, I think, not all is necessary complexity. I think. Yeah.
So there's no virtual memory, user kernel mode, TLB.
I mean, in Haskell there is, yeah, but not
in Cloud.
Yeah.
I see. Yeah. All right. Thank you.
Ryan Scott from Galwa. So while you were presenting your RISC-V machine type class, it struck me that despite the fact RISC-V was in the name, most of the methods in the type class were very general, and without knowing much more, it seemed like it could also apply to other instruction set architectures like x86 and ARM and so on. Have you thought, like, would this be a suitable approach to generalize to other ISAs? And if not, what sorts of challenges would arise if you tried to do that?
Yeah, good question. I simply don't know because we didn't try. And people tell me that ARM and x86 are much more complex. I don't know what kind of stuff would come up. But certainly, instead of calling it RISC-V machine, I could call it machine and then maybe tweak these primitives a little bit and maybe it would work. Yeah. But yeah, to be tried out. Yeah.
Cool, thank you.
Ben Gamari, well typed. I had actually almost the opposite question of Ryan over there. I was looking at that type class you had, and I saw, okay, set, register, load, word. These are all things that clearly are part of the architectural state of the machine. But then I saw commit further down the line, and it seems like, it sounds more like a microarchitectural detail. And I wasn't sure whether, maybe my knowledge of RISC-V is not very complete, so that may just be my misconception. But how much of that type class is really just read off from the architectural state, sort of specified by the specification itself, and how much was more incidental?
I think there is a thing of to be said if you run into an exception or something, then the state that your previous instructions have modified actually doesn't get is discarded, and I think it's related to.
Okay, so that actually is architectural state then.
I think so. Yeah.
To do
yeah.
With. Okay.
It's
great.
not a commit. It's not a commit in the sense of I don't know, a pipeline implementation detail or something.
Right. Yeah. That was what that invoked. But
Yeah.
okay. No. Great. Thanks.
Hi, Neil Krishnaswamy from the University of Cambridge. I wanted to ask, since sort of we have two machine checkable formalizations of RISC-V now, the SAIL and yours. Have you tried doing any like sort of differential testing to shake out bugs in either one?
Yeah, of course. That's a question one has to ask. Yeah. No, we haven't. We haven't even tried. It's maybe a bit of a problem of academia. It's just not academically very rewarding to do the work. So if you're a somewhat smart PhD student, you're not signing up for this. But yeah, I mean, it would be very interesting to do and to see whether it works and to see whether it reveals differences. Yeah.
Okay, thanks.
Christian Bai from QBayLogic. So RISC-V spec is two documents, the privileged and the unprivileged execution. And I was wondering, so in this work, did you look at whether you can, by accident escalate from user to machine or from user to super user kind of things? Is that part of the spec that you checked?
Yeah, we have set privilege and the control and status register instructions we did model that stuff in Haskell certainly, and in Coq a little subset just good enough for one project. But we do have like privilege, machine mode, user mode, or whatever these 3 or 4 levels are, and the corresponding control and status registers, and yeah.
We haven't proved any meta theorems about you can't accidentally upgrade
that was my question.
Oh,
so
okay,
how much of the when you're creating a CPU, like doing the first part, the non-privileged, like do I do add correctly or do I do jump correctly? That's fairly easy, but making sure that you don't violate the other one, that's the hard thing to do.
I mean, for concrete programs, we can prove that after we didn't do it, but we could prove that privilege levels remain the same, or even for abstract, basically for programs which only contain this class of instructions, we could also prove meta theorems like that. We just didn't, but.
All right, thanks.
Hi, Hi, Katie Casamento from Portland State University. This is actually just a really very minor comment that's not as interesting as any of those questions, but I noticed that you said since you're using an embedded DSL in Haskell, you're not able to sort of override or overload the if-then-else syntax or the let-in. I believe you can override the if-then-else in particular with the rebindable syntax extension. And so what happens there is that an if-then-else kind of notation gets translated to a function call to a function called, like if-then-else. And I believe it is valid to overload that in a type class. So I hope that's helpful.
Oh, thank you. Okay, good to know, yeah. Can it, more importantly, does it support let?
I don't think it does, no.
And that would be pretty important.
That's the disappointing.
Yeah.
I have additional question. So the semantics, the semantics RISC-V you extracted to Coq, how general purpose is it? For example, if I'm writing compiler from C to code generating RISC-V, can I use your Coq-generated semantics to prove compiler correctness?
Probably. I mean, I wrote one compiler which goes from a C-like language to this RISC-V Coq specification, and then probably you can too, I would assume. Yeah. I mean, we have one compiler, doing it. Yeah.
You can write, but can you prove? You think?
Sorry?
Can you use it in proofs?
Yeah.
Okay,
By verified, I mean I use this thing. Yeah, it's all verified. Yeah.
All right.
Yeah.